If you ask me, so like, which one of your posted lectures does this most closely follow? I think the honest truth is none. I don't think, as far as I can find anyway, if I have written these things down in a posted PDF, I can't locate them. And so like, if you look at the next lecture that we haven't already covered on that thing that just happened, you'll see that I jumped straight into examples about collisions and momentum and things like that. Of course, are interesting, but before all that, we should really talk about center of mass, right? So, well, I mean, I don't know. Maybe you should talk about momentum first, chicken or egg. I don't know. I'm going to talk about center of mass today. So, to start with, two masses, M1, M2. The center of mass for two masses is defined relative to some coordinate system. All right. So I have some system of coordinates with which I'm defining the center of mass. So the center of mass is based on the mass of the first particle, the mass of the second particle, and also, importantly, the position vectors of these particles. Let me call the position vector of M1 R1. True. The position vector of M2 I will call R2. All right. The center of mass R. Center of mass. I'm just going to use capital R for it today. Just to have a notation for it. It's not too annoying. What it's going to be is it's going to be 1 over the sum of the masses, M1 plus M2, times M1 R1 plus M2 R2. So what this is it's a weighted average. Well, I guess to make it a properly weighted average, I'd have to multiply the top and the bottom by G. Joke. So it's a massive average at the moment, I guess. I mean, it's so each, the more mass you get, the more the more prominently the first position vector figures into this, and then you divide by the total mass, right? So you can talk about what's called let's see, there's the center of mass. You can also talk about, if you take all the masses to be the same, you get back to something more geometric, which is what? What does this flash do when the masses are equal? What's this give you? This is equal to the midpoint. Right? It just gives you the point directly between the two.
Should be R1 plus R2 over 2.
Yeah. Precisely. So, and that there's all kinds of fun applications to this. So, for example, suppose I have like a tetrahedron, right? And suppose I want to find the point in the center of the base of the tetrahedron. Call it C. Well, that's easy enough to do if I have the position vectors, say P1, P2. Maybe I should use R1, R2, R3. Maybe I could just stick with the same notation for like 3 minutes. R2, R3. Then C would be actually just 1/3 of R1 plus R2 plus R3. So this idea also has use in geometry, right? For example, if you want to find the height of the tetrahedron, I find it useful to use that center point of the base to figure out the height to the top of the tetrahedron.
What are we using as an origin in this coordinate system?
I didn't say. Doesn't matter. I mean, whatever I choose as the origin, this calculation is still true. I mean, whether I base the vectors from, you know, from here, you know, or if I had the origin over here, it wouldn't change the fact that that's the center of the base of the tetrahedron. Now that would be center of mass of what? Like if I had three masses, M1, M2, and M3, right, to get center of mass. So let's shift gears here a little bit. If I have three masses, right, if I add a third mass to my initial picture here, right? Oh, I'm getting bored with this. Why don't we just add n of them? The nth mass, right? And suppose that each mass is respectively at position. You know, the jth one in here somewhere, there's an n sub j. That one is at position vector rj, all right? Then you can talk about the total mass of the system. Right, the total mass, we use big N. Total mass would just be the sum. J equals 1 to n. I know you've seen this notation before. You're in Calc 2. At this point, you should be suffering series and sequences, yes? Yeah. What's that? Limit? Limits? Oh, limits of sequences. Ah. Hey, but by now you've had Calc 1, so you already saw the Riemann sum. So surely this notation is not new to you. Right, so sum j equals 1 to n, m sub j. That gives you the total mass, right? And then the center of mass vector is just 1 over the total mass. You have to weight, sorry, I mean, I can't. Mathematically, we're weighting by m. Physically, that's kind of an atrocious statement, but anyway, you can deal. J equals 1 to n of m sub j, r sub j. So that's just the, there you go, that's the definition of the center of mass for finitely many particles. ¿Es bueno? Okay. Shall I do an example? Let me do an example with numbers and such. So, for example, if I have M1 equals to 10 kilograms at 1, 2, 3 in meters, and if I have M2 equal to 20 kilograms at -1, -1, -1 in meters, and if I have M3 equals to 30 kilograms at 1, 0, 0 in meters, then I can ask what's the center of mass for this system. So if you were to see this question on my next test, you should say, please, sir, may I have another? I mean, this is a gift. This would be a very, very friendly question. Probably one that you wouldn't find me asking, but who knows? All right, so what's the total mass? 60 kilograms, right? Total mass is 60 kilograms. Then I do 10 times 1, 2, 3. And let's just forget the units if you don't mind. I'm going to erase that kilograms. Because what we're going to have is we're going to have kilograms over kilograms are going to cancel. Let me save myself some writing. 10 times 1, 2, 3 plus 20 times, what's that?
Why negative?
Why
Is
negative?
that negative or just divide the little thumb right?
Oh, where it is.
Oh, that was a, yeah, sorry.
Oh, okay. Sorry.
And my fault. -1, -1 plus 30 times 1, 0, 0. And then feeling guilty for not putting units in, I will put them in now. Times meter. What's up with this? Yeah, whatever. And then you guys can add vectors, right? So this is what, 1/60th? What do we got? 10 minus 20 plus 30. 20 minus 20. And 30 minus 20. So I get 1/60th of 20, comma 0, comma 10 meters, or finally cleaning it up just a bit, 1/3, comma 0, comma 1/6 meters, and then I'd probably leave it as a decimal, but I'm going to be lazy. There you go. Now, if I was so foolish as to attempt a graph, I will foolishly attempt that now. This will always go badly for me. 1, 2, 3 is where? It's like, roughly speaking, here is my M1. I can't draw anything. Why did I even try? Wrong with me. M1 is roughly speaking there. M2 is at -1, -1, -1. Oh man, that's sort of down here. M3 is at 1, 0, 0. That one I think I can do. Right? And like M3 weighs 3 times as much as M1, right? And M2 weighs twice as much as M1. So clearly M2 and M3 are where most of the mass is centered, right? So the center of mass ought to be somewhere close to these two guys, which is what I found, is at 1/3, 1/3, 1/3, 0. So it's somewhere like here is actually the center of mass. Right, it's at z equals to a sixth, and that's not quite right. It's x equals to a third. It's like right here. Now let me tell you what we're going to prove. What's the meaning of the center of mass? Like, what is it? Besides just being this thing we can calculate, and it's kind of relaxing to calculate these, right? What the center of mass is, conceptually, if you were to take these 3 masses, right, and just treat them as one single mass, it's in fact correct to think of this system as a single mass, the total mass m, big M, as if that was just one mass at the center of mass. That's what this system is. If you ignore the internal motions coupled between 1, 2, and 3, just think of it as a single entity. It's as if you have a single mass at that center of mass point. If these were somehow tied together by light rigid rods, that they were like their relative positions were fixed by some rigid set of rods, and you were to take these and throw these through space, what you'd see would be that 3 masses rotating around that center of mass point. That's how it works. So there's great physical significance as we'll soon discover. So I think you guys can do problems like this. Yep.
Is it possible to, given functions for volumes, to use it infinitely? Use this a variation of this function infinitely?
Thank you. Very good question. That was my next thing. So what happens if you have infinitely many masses? In fact, that is the next chapter in this story. So of course we're not content to work with finitely many masses, right? So you might ask the question, what happens if instead of having a finite number of masses, right? What if instead of having a finite number of masses you have an arc? Some sort of distribution of masses, right? So in that case, you should have something like R is equal to 1 over the total mass. And the summation, what happens so I mean, heuristically speaking, instead of thinking about M, you can think about dm, the infinitesimal mass at some position vector, let's say R, right? And so what this becomes then is the integral over the blob of R dm, where the total mass is the integral over the blob of dm. So the finite sums become integrals. You say, well, what kind of integrals? Well, it depends on what kind of blob. Talking about a 1-dimensional blob, a 2-dimensional blob, or a 3-dimensional blob, right? 1-dimensional blobs are the kind I can ask you about in here without taking off without putting bumpers on the alley, let's say, right? The 1-dimensional ones you have the calculus you need to do already. So for the 1-dimensional case, we'll start there, okay? one-dimensional case, we'd have something like this. Some kind of stick or something like that. And there's some kind of mass distributed along it, right? And I usually use a lambda, this Greek symbol. Lambda is equal to the mass per unit length, or dm dx. Okay? So if I have lambda, which is dm dx, over some finite, like, here's x, say it goes from, say, x1 over here to x2, then you can ask, what's the center of mass of such a stick? Oh. That will not happen again. Now, you guys already know the answer. If the mass per unit length is constant, where's the center of mass of the stick?
Midpoint.
The midpoint, right? But if it's a function of x, then it could be other places, is the point. Right? So, excuse me. The total mass then, in this case, would be integral from x1 to x2 in my setup of lambda of x dx, or just lambda dx, just to be less confusing perhaps. And then the center of mass, x center of mass, would be equal to 1 over m, the integral of, well, from x1 to x2 of lambda x dx. The reason for that is simply this, is that like m dx here is equal to, x times dm, right? Which is sort of like the RDM, all right? X dm here is x times lambda dx, right? Because if lambda is dm dx, then dm is lambda dx, right?
What is dm again?
The infinitesimal mass at m, at x. So if I pick the point here at x, then this little tiny bit of this stick, this little dx, segment of this little infinitesimal little bit, that's subtended by dx. According to that dx, there's a little bit of mass dm there. And the proportion is given by lambda. Lambda is a function possibly, but not over dx. Over dx, the lambda is constant. Because the lambda can't jump values over an infinitesimal range. All of these heretical mathematical statements, of course, can be replaced with careful limiting processes, blah, 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 fine print here. Okay, so, so for example, let's suppose we had something like, maybe you had something like this. So lambda of x is equal to, I don't know, something like alpha x. Or 0 less than or equal to x less than or equal to L. Where alpha is some constant. So this basically is sort of a naive model for something like kind of like a needle. It goes to an infinitely sharp point and then it kind of like gets bigger. It's not exactly, I mean it's a wedge. So you can ask what's the center of mass of such a thing, right? Now, so first of all, what's the total mass? I integrate from 0 to L, alpha x dx, what do we get?
Alpha L squared over J.
Indeed, there you go, that's the total mass. And then we should calculate center of mass. I'll do that right below it. Will you be able to get it, Jess?
Yeah, you said that's basic.
Okay, so x then, center of mass,
equals the integral from 0 to L. Well, sorry, let me put 1 over m there. So 1 over big M, integral from 0 to L of what? Of alpha x squared dx, right? Because I have to do lambda times x, but lambda is alpha x, so this is x times lambda is alpha x squared, right? Everybody with me? When lambda is alpha x, x times lambda is alpha x squared. And so the integral 1 over m alpha x cubed over 3 evaluated from 0 to L. And so I get 1 over m, which is, by the way, what? It's 2 divided by alpha L squared times alpha L cubed divided by 3. You see what happens? L squared and the L cubed simplify. The alphas cancel. And we're left with what? 2/3. Oh, alphas don't cancel, do they? Wait a minute.
Maybe it's a constant.
Yeah, they do. I'm an idiot. So apparently 2/3 L.
So that means that if the lambda is equal to an x function, will the alpha always cancel if it's just x? Or does the alpha really not matter at all? I guess if it's constant.
I like it. It's weird.
Oh wait, no, but well, we're looking at. Looking at that triangle, so it sort of makes sense.
So what we're looking at right now is the shape is defined by
I mean, math is what it is, but I was thinking it should depend on alpha. But
the shape that we're looking at right now is defined by lambda of x and the x-axis.
well, I'm just drawing a shape.
Yeah.
I'm pretending like the mass per unit length is coming from having more of the same stuff. So I'm intuitively like identifying it with having a stack of cheese, let's say, something with uniform density, and just having more cheese over here than over here, which means as x increases, I have more cheese stacked there. And I'm just like identifying this two-dimensional object with just this sort of bottom line as if there was more mass just there. Yeah.
Well, I think then what you've done is you've set your slope equal, y equals x, because that's the variable, the slope of the weight. So as you continue, you've got a triangle, spreading. I think that answer makes sense then,
Okay. Good.
because it'll be not a symmetrical.
Yeah, I mean, I found this before. I shouldn't be surprised by it, but I don't know. But okay, so that's an example. One-dimensional, basically, just integrate the density with respect to x, right? Now, how about two-dimensional examples, though? Now, there are some two-dimensional questions I can ask you, which you should be able to just figure out by this thing called common sense. All right, so two dimensions. For example, if I was to ask you, here's an annulus. So the two concentric circles, one at R1, the other one here at R2, right? Radius R1, radius R2. And I was to tell you that this, and the symbol I typically use for area densities is sigma. So sigma is dm dA. All right, suppose that was equal to a constant. Where's the center of mass?
Exact center.
What's that? It's exact, yeah. So the center of mass for this, it's right there. Exactly. Your intuition is correct. I mean, center of mass is a good term. It makes sense. I mean, it's an intuitive term, right? Now, there are fun things you can do. Like you can sort of go half infinite half finite. So one fun thing we could do is say, okay, suppose you have another mass, and so suppose I have total mass m on this thing, okay? Let me say m1 actually. So I have m1, and we agree that that's effectively a particle at the origin of mass m1, right? I could throw in another particle to make this example more interesting. Over here, I could throw in m2 at position, L comma 0. Right? And then I could say, what's the center of mass for this system? And it is valid, in fact, mathematically, to say that the center of mass, so I shouldn't say, I should say, now that I'm doing this, I should call this R1, right? So the center of mass would be 1 over m1 plus m2, m1 times, zero. Not excited. Weird. Plus m2, right? Times L0. So in fact, the center of mass for this would be m2L divided by m1 plus m2, comma 0. It's always somewhere on the x-axis.
Is that a vector? Or
What's that?
matter?
Oh, you can think of it as a pointer or a vector. Whatever floats your boat. Here you go, buddy. Put your arms over it. There you go. Long day. That makes sense. I mean, in the case that M2 is very, very small, right? It's essentially just at the center of this annulus, right? And on the other hand, if M2 is really big, this fraction tends to just L, so that means that the center of mass goes over here. And then otherwise it's somewhere in between them. Yeah. If you ask what's the center of mass, for example, of like the sun and the Earth system, the center of mass is actually somewhere inside the sun, because the sun is just that much more massive than the Earth. 10 to the 30th versus 10 to the 24th kilograms. It's like a million times more massive, right? So, and also the sun is kind of big. Yeah.
So the greater the distance between them, though, the larger the coordinates get. Does that make any sense?
Yeah, this is true. The greater the
From
distance,
origin.
the further M2 is for a fixed mass.
Yeah.
The farther away M2 is, the more the center of mass gets pulled that direction. Yeah. Linearly so. Yeah. So okay, but you're saying, okay, well, what if the density is not constant? Then what do you have to do? What's the honest truth? Oh. I'm going to erase this. Your integral over the blob has to become a double integral. So if, to be honest, if I have some laminate in, say, the y-x plane, right? And I have sigma as a function of x and y, so here sigma is equal to dm dA, then to find the net, to find the net mass of this region, I need a name for it. Let me call it mass. So the mass of S is equal to the double integral over S of sigma dA, where this is a double integral, as you might learn about in Calculus 3. I mean, you will learn about it in Calculus 3. Whether or not you've learned about it yet, I don't know. Whatever.
That was today.
Oh, really?
Yesterday.
Ironic. Or I should say ironical. Let's see here. One of my absolute favorite sayings of Dr. Wing. All right, so, and so that's, I do love Dr. Wing very much. He's fixing my computer as we speak. I mean, my wife's computer. she needed a gaming laptop. Let's see here. So, so now you have x is equal to 1 over the total mass, and you do the integral over s of x sigma dA, and y is equal to 1 over the total mass of that integral over s of y sigma dA. You know, honestly, folks, even these are not totally general. Like in Calculus 3, you learn about a scalar line integral at the end. That's really what you should talk about for the center of mass, for example, of a wire that goes through space. Or for two-dimensional, really you should think about a surface, which could be like a rubber surface that bends. There you need the scalar surface integral. So even these things I'm telling you aren't entirely general. But that's what you do. But you know, I could give you examples where you don't need all of this to do it, right? Like, for example, you've got something like a square, right? Not a square, but well, yeah, let's say a square of side length L, right? And I could make the area density depend on the position in a slightly non-trivial way. So I could still make it, it's a two-dimensional problem, but I could kind of make it a one-dimensional problem. Here's how I do it. I would tell you sigma of x comma y, it's equal to some constant. We can think of like alpha, let's use alpha, times y. Okay, so it's constant. It's constant in x, but it depends on y, like this. So what this means is this laminate in the xy plane, this you know, two-dimensional solid. It's skinniest at the bottom, and it's heaviest up here, so to speak. Right? It's more mass. There's more mass up here, and less down here. Goodness gracious! I believe from that example we can anticipate that the center of mass is where.
2/3 of the way up.
2/3 of the way up. Yeah, I hope so. Let's see how to work that out. Or make it more exciting. Should I leave it as alpha, or should I make it alpha squared to make it more exciting?
Well, to make it alpha.
I'll leave-
Infinity
Being my taught teaching me a lesson to ask questions in class. I'll learn my lesson actually. So what I would do is I would chop it up into pieces, chop, into pieces that I could handle. So basically here's a piece I can handle like this. What's dA for here? What's the dA for this? This is, take back to Calc 1, what's dA? What's the width of this? The height of the strip is what? It's dy, right? What's the width of the strip? L, right? So L dy is dA, right? So then dm is sigma dA, right? So dm is what? It's alpha y L dy. That's the little bit of mass in that one horizontal strip. So if I want to calculate the total mass in this square, what do? Add them up, right? And the way we add things up in a continuum is to integrate. So total mass then integral from 0 to L dm, but dm here is alpha y L dy. Of course, the alpha and the L are constants, so I have alpha L over 2 y squared evaluated from 0 to L. Of course, we get alpha L cubed over 2. There goes total mass. Excuse me. How about x?
What does x stand for in this?
The center of mass for the x.
So, and then when you find both the center of mass for the x and then y, how do you relate them?
Well,
like
you put them in,
Coordinates.
they're coordinates to the center.
Yeah, I mean, so here somewhere is X center of mass. That's a very good question. Y center of mass means we're trying to find the coordinates for the center of mass.
Okay.
So X center of mass, that would be the integral over S as this thing is S, quote unquote. So 1 over m integral. I'll write down double integral of x sigma dA.
Now I could go through the gory details of setting that up, but can you see what the deal is with x as you integrate it over this shape? It's negative on this part. It's positive on this part, right? So, and there's complete symmetry. It has the same values, negative here as it has positive here. When you do this sum, you get 0. I mean, more to the point, it's clear by symmetry that the center of mass is on the y-axis. So this integration must be 0. We don't need to do it.
But if it was not, how would we do it?
We'll do that with the y in a second.
Yeah, we'll do 1 with the y. So y center of mass, 1 over m. So we have to do, and so we figured out that dA was this, right? So the integral of, let's say, y sigma dA works out to 1 over m. As we can see, it's actually the same as just integrating from 0 to L of alpha y y squared L dy. See the this sigma dA was my so-called my quote unquote dm, right? So dm I worked out over here. dm is alpha y dy. So here's the dm, and then this extra y gives me that y squared.
And what happened with the double integration?
I'm saying that this double, I mean, just think about adding together these things. It's the same as just integrating these strips. In other words, I'm not really doing the double integral. I'm trading it for an equivalent one-dimensional integral. Don't worry, I'm not going to teach you guys double and triple integrals in here. I will do only special versions. Why, you want me to do double and triple integrals in here? I could be pushed. I mean, I'm not averse to it. I think they're fun. Do it. Yeah, they're fine. Okay, so 2 over alpha L cubed integral. So this is alpha y cubed L over 3 evaluated from 0 to L. What do we get? 2/3, the alphas cancel, and we get L to the 4th over L cubed, which is L. Yep. So, as predicted, the center of mass is right about there. Now, the reason that it's higher in the shape, right, is because we were saying that the mass density is not constant. It's larger towards the top of the shape and smaller towards the bottom. Right? Yep.
So, in effect, are we more or less looking at a pyramid with the base at the top?
Yeah, it would be something like that. It would be like an
Upside.
upside down wedge.
Finish next.
Yeah. Yeah. Oh, 3 dimensions. Yeah. So what I'm trying to tell you guys is if I ask you something that actually requires integration, there should be some sort of like simplification of the area of the shape, which actually allows you to like break it back down to a one-dimensional problem. So you don't actually have to do an honest to goodness double integral, which requires like full Fubiniing and all that junk, which is not that hard.
as you shall soon see, for those of you who are there. Oh, I'm looking for this. You know what? Forget about 3 dimensions for now. I'm actually going to show you the physical significance of the center of mass instead. So let's see if we can discover in a couple minutes. We're going back to the finite case, all right? All the arguments I'm about to give over finite sums, you can easily extend to integrals. There's really not much loss of generality here doing this. So, you know, physics, in particular, kinematics, and dynamics, or center of mass. Okay, so our starting point is simple. It's just that the center of mass, R, is equal to 1 over m sum j equals 1 to n of m sub j r sub j. All right? So differentiate. dr dt is equal to what? 1 over m. And so basically just using linearity of the derivative and assuming that the masses are constant. The masses aren't constant. That's another problem entirely. But here we go. So what does this say? This says that the velocity of the center of mass, right, is equal to basically the same weighted sum, right, of the velocities of the particles respectively. So to find the velocity of center of mass, you just take the velocity of each particle and multiply by the mass of the particle, add those together as a vector sum, divide by the total mass. That's the velocity of center mass. It's very natural. What happens if you differentiate again? Again, assuming the masses are constant. Or if you like, you could say, what is that? That's 1 over m. The sum j equals 1 to n of m sub j, a sub j, right? Where a sub j is the acceleration of the jth particle. So folks, what can you say about the jth particle of mass times the acceleration, mass of the jth particle times the acceleration of the jth particle, which is the product of m times ab for that jth particle?
Force.
The force on the jth particle, right? So this we can replace with the net force on the jth particle, right? And if I multiply this by m, but you say, what is this, by the way, you know, main style here? This is dv, center of mass, dt, right? So this is, by the way, the acceleration of the center of mass, right? And so, tilt your head and squint, you can see that the total mass times the acceleration of the center of mass vector, right, is equal to a sum, j equals 1 to n, of the net force of the jth particle. In other words, the net force on the system. This is what I claimed at the beginning, that you can replace the n particles with a single particle of total mass m at the center. And it's as if you just have that one particle subject to ma equals to f as usual. See? Notice what we found in the end, this guy? Nothing about the internal workings, right? there's there's more to say about this. Well, I could say one thing. This thing is so important it has a name. And if you multiply m to the other side, what you get is m times the velocity of the center of mass, right? Is equal to sum j equals 1 to n, mj, bj. By the way, mj times bj, this is the momentum. Of j particle. Whereas the total mass times the velocity of center of mass is the momentum for the whole system. And from this calculation that we've done here, you get the following. If the net force is 0, right? For some system, then what? ddt of what? ddt of well, ddt of the momentum, really. Sorry, a little sloppy here, but it's not hard to see that from the calculations we have on the board, that the net momentum. I still have 3 minutes, let me do it here.
All right. So, acceleration.
Let's see here. So if the net force is 0, that gives me right here. So F net is equal to d total mass times the acceleration of the center of mass, right? But that's equal to the total mass times the time derivative of the velocity of the center of mass. But you can rewrite that as ddt of the total mass times the velocity of the center of mass. But if you look at the formula for the velocity of center of mass, if you multiply this by m, what do you get? Multiply this by m, you're just left with ddt of the sum j equals 1 to n of m sub j, v sub j. So if the net force is 0, this thing in right here is called the net momentum. This is the total momentum for the system. This shows that if the net force is 0, then the net momentum is conserved. Right? And this is how we're going to solve collision problems next class. So in a collision, you have something like 2 masses, M1, M2. They come in, bang, stuff happens. Well, M3 and M4 might come out, I don't know. They might, maybe, you know, the cars get smashed and one person gets thrown to the other one, I don't know, whatever, all kinds of junk can happen. Anyway, before, after. But the thing is, if the collision happens if this is over a really short time scale, then there's not enough time for the momentum to be changed. So you end up with it. You get momentum conservation even over collisions because they happen over such a short time scale that, I mean, another way to write this is that the change in net momentum is equal to the net force times dt. So if this time scale is so short, even if the net force is big for a short, the net force, the external force here is never big, but in a collision. But if the dt is small enough, you can still have dp being 0. In other words, the momentum doesn't change over like a collision. And so this is I'll go into more detail about this next class, but this conservation of momentum is really important. It's more general. Energy's not always conserved, okay? But momentum is conserved. So at least over collisions, over short timescale collisions, which is most of what we do. And that's what we're going to be talking about a lot in the next few weeks, is this notion of momentum. So, I shut up. Have a good weekend.